Just try to make a quick video about some review for several topics for the upcoming test. I'm using Ms. Frio's packet here. I guess I'll start with the things that I think are least familiar, that might be newest to us, just to make sure you hit those high points on the new things. So first of all, there's a page in her packet where you see electromagnetic spectrum here on the left, and I have written a list in order of different types of electromagnetic radiation here. So on the left, maybe you can see that I have an E over there, and that E stands for energy. And so what I'm saying in this, the way I've listed these, is I'm saying that the energy is increasing as you go from bottom to top, and notice also frequency is increasing as you go from bottom to top. These are the different types of electromagnetic radiation in the electromagnetic spectrum. Electromagnetic waves are electrical and magnetic in nature, and the electric and magnetic fields create each other as they change. So, the longest wavelength, I forgot to mention that on this right side, we have wavelength with my arrow for the amount of wavelength. You're going down on the page where the energy and frequency are going up. So this shows us that as the energy and frequency increase, the wavelength is actually decreasing and vice versa. The longer the wavelength, the lower the energy and the lower the frequency. So radio has the longest wavelength, radio waves, like we listen to sometimes in the car maybe. Those radio waves are the longest of the light spectrum. All of these are kinds of light, but most of them are invisible to us. Radio has the longest waves, the lowest energy, the lowest frequency. Microwaves that we cook our food with in the microwave, that ironically cooks food faster than infrared, they're actually longer wavelength and lower in energy than infrared. Even though infrared is what is used in like a conventional oven or a fire. And then what we can see starts with red. That's the lowest energy, lowest frequency of the visible light. And red is the longest wavelength. So we're going up in energy as we go from red to violet, but we're also going shorter in wavelength as we go from red to violet. Then just outside the range that we can see is ultraviolet, and the ultraviolet just above the visible range, just beyond the violet end of the visible range, is the kind that can actually, give us sunburns and things like that. It can be damaging. More damaging than that would be X-rays, and finally gamma rays would be the most damaging, the highest energy, the highest frequency, and the shortest wavelength of all electromagnetic radiation. So what you can see if you move over here to the right is that we're looking for inverse relationships in the first little section here and direct relationships in the second. So as we showed over here on the left side, I'm back over on the left side, my cursor's tracing up the energy arrow, and as I went up that arrow, we were shrinking the wavelength. So energy and wavelength are inversely proportional. The greater the energy, the shorter the wavelength. The shorter the wavelength, the greater the energy. And frequency and wavelength are also inverse. And of course, this should make sense to you if you remember the speed of light formula, which said C equals F lambda. You can see that a constant, the speed of light, is equal to frequency times wavelength. That means when the frequency gets bigger, the wavelength must get shorter, and when the wavelength gets bigger, the frequency must get lower. And then, if you remember that E equals Planck's constant times frequency, that was our other formula there, you can see that as the energy goes up, the frequency goes up, right? So if frequency and energy are directly proportional, like it shows here in this direct relationship, then when either one of those increases, the wavelength decreases, and vice versa. So all radiation types shown on the electromagnetic spectrum consist of different types of light. Only a small portion is visible to our eyes. That's what's deceptive over here. I expanded out Roy G. Biv, but that made it take up way too much space. Light is a particle. It's a photon made of photons and a wave. Thus, it has a specific energy depending on the type of light. Red light has a longer wavelength but a lower frequency. Violet light has a shorter wavelength but a higher frequency. Therefore, violet light has more energy then red light. Okay, here we were supposed to list these different colors or frequencies of light in a particular order here by increasing the frequency. So we have to go from lowest to highest. So the lowest frequency we see is radio, and the highest frequency is gamma. So it goes radio, then what's next? Radio, then in this list, infrared, then we'll hit the yellow, then the green, then ultraviolet, and finally gamma. And decreasing energy. So we're starting, number one will be the highest energy, and number two a little lower, and so forth. So the highest energy is gamma, next is UV, next is green light, then yellow light, then infrared, then the lowest energy is radio. The decreasing wavelength should be the same as the increasing frequency, because decreasing and increasing are inversely proportional to each other, but wavelength and frequency are inversely proportional to each other. So that's why that works. That was newish, and so we needed to cover that. Let's see, anything else here we really need to do? This is just a quick review. We know this stuff, but here it says John Dalton's postulates. Are they true today? And I've just struck the things that aren't. It says atoms are the smallest piece of matter. Well, no. We've been able to break things down. Electrons are one of the smallest pieces of matter. And it says they're indivisible. Well, obviously, if we're pulling electrons out of atoms, atoms are divisible. So he was a little bit wrong on that. So we put an X for not true today. Atoms of different substances are different from other atoms of other substances. True. Changing the number of atoms changes the substance. No, that's not true. And all atoms of the same substance are identical. We struck through identical because we know about isotopes, right? Isotopes, which are atoms of the same substance, but they have different masses because they have different numbers of neutrons. Finally, atoms will rearrange themselves to form new substances during chemical reactions, and that is true. Okay, Rutherford's experiment determined positive particles are in the center of an atom, and the rest of the space is mostly empty, with some electrons whizzing around. All right, that's actually review there. Let's go back up and see if there's anything else we need to cover just really quickly. I think we've done this all, but let's just do a little more review. Okay, remember Dalton, the 5 postulates we just looked at. His atomic model was the billiard ball model, thinking the atoms couldn't be broken. They were very rigid, hard, and impenetrable, indestructible. Thomson came up with his plum pudding model using the cathode ray tube. This is supposed to be just a portion of that, and I chose to label this bottom plate as positive, this top plate as negative, and what I'm showing here with the red line is the beam that got bent when it got attracted to the positive and repelled by the negative. Over here is supposed to be the gold foil experiment. These paths, these arrows, are supposed to be the directions of the travel of alpha particles, which are helium nuclei that were positively charged and quite heavy, as radioactive materials anyway go. And you can see that some, very few bounced. And you can see this arrow went in, hit, and then the arrowhead is going away, but back in the direction from which it came almost. So, and that experiment was the gold foil experiment. This is what would have happened when the gold foil right here. The gold foil would have been along here, vertically. And those lines that are crossing were the paths of the alpha particles as they travel through. Bohr, we talk about him. All you need to know right now is that his model is called the quantum mechanical model. It became way more developed after him, but he realized he was able to interpret the hydrogen emission spectrum and explain it, like why hydrogen gives off these particular patterns of light the same every time. And so it was that one of the experiments that would prove that is the gas discharge tubes that have a particular gas, just one gas inside, and then when you electrify them, they give off particular patterns of light, spectra of light. Chadwick, we didn't have to talk about, but he figured out that a massive neutral particle exists, or that massive neutral particles exist in the nucleus, prior to him, they like at Rutherford's experiment, they didn't realize that there was something besides the positive stuff in the nucleus. Yeah, there was something else. It was neutral. They were subjecting something to some like a wax, to something that they thought was just a radiation, like a wave, but it was knocking protons out. And so he figured out that what they thought was just waves or a beam of something was actually these particles that had to have quite a bit of mass if they're able to knock a proton out, kind of like a billiard ball would knock another billiard ball out. And so he figured out that these things, the reason people thought they were radiation was because they didn't respond to positive and negative fields. That was because they were neutral. But he figured out that they were actually neutral particles, not neutral radiation, like a beam or a wave, and that they were actually about the mass of that same mass as a proton. That's why they could knock protons out. So here we have a little summary of some ideas. We're talking about particle location and how do you find the amount. The protons, they're located in the nucleus, and you find them from the atomic number. Electrons, they're in the electron cloud, and they have to equal the proton number, which is the atomic number. Neutrons are in the nucleus. So notice in the nucleus are the protons and the neutrons. And you take the total mass of the atom minus the atomic number, or that's the number of protons, and that'll find you the number of neutrons. And then finally, just mass as a total. Well, most of the mass of the atom is just the protons plus the neutrons. So if you add up the number of protons and the number of neutrons, you pretty much have the mass of the entire atom, and all of that mass is in the nucleus, except for those tiny electrons with their really, really tiny masses. Here's a bit of symbol notation. Chlorine 37, that's one of the isotopes. It would, of course, have 17 protons because every chlorine has 17 protons. And carbon here is carbon 14. This particular one, so carbon every time has 6 protons, but this one would have 8 neutrons to get a mass of 14, and this chlorine would have 20 neutrons to get a mass of 37. If we write mass notation, we just write the element name dash the number for the mass, and the element name dash the number for the mass for mass notation. Here we can go quickly. I think you can do all these really fast. We know that in copper, its mass is listed above, and this is the nuclear notation. And 29 is the atomic number. So 62 minus 29 means 33, so that's how I got that number of neutrons. And of course, in a neutral atom, the number of electrons and protons are identical. Silver, if you look it up, has an atomic number of 47, which means 47 protons in the nucleus and also 47 electrons in the electron cloud. If you take 47 away from 117, this isotope of silver would have 70 neutrons in the nucleus. This cobalt here, we were given that it had 42, that is cobalt. So of course its atomic number is 27, so it's got 27 protons. A neutral atom of it would have 27 electrons. And if 42 is the number of neutrons, actually, I've got an error here that I need to fix. We'd have to take 42 plus 27, and we'd get something like 69 be the number of the mass. 69 would be the mass of this cobalt. Next, we have something that had a number of protons as 9, and that's the atomic number, which cannot change for any element. So that must be fluorine, which has an atomic number of 9. If it also has a mass of 18 and it's got 9 protons, it must have 9 neutrons by subtraction, right? 18 minus 9 is 9. And of course, where there are 9 protons in the neutral atom, there will be 9 electrons. Neon, here it says neon 21. Well, we know neon's atomic number is 10. If its mass is 21, then it must have 11 neutrons. Here's sulfur. We're given that it has 17 neutrons. Every sulfur has 16 protons, so that means its mass is 33. Here's argon. It tells us the mass is 39. It tells us the number of neutrons is 21. If you do the subtraction, you get 18. 18 tells us that must be argon, because the atomic number of argon is 18. Energy levels. I'll get more into this later. You don't have to know this thoroughly yet, but it might be beyond what you already knew. In the first energy level, the maximum number of electrons is 2. In second energy level, 8. Third energy level, 18. Fourth energy level, 32. Here's a Bohr model. We're told that lithium is 7. That's this isotope of lithium. Of course, the atomic number of lithium is 3. Then the number of neutrons must be 4 by subtraction. 7 minus 3. Okay, I feel like you're already all up on all of that. So there's nothing more to review here. Although I do need to talk to you about gas laws to prepare you for the test.